Yeah, and, thanks very much to the organizers. Fantastic meeting. Thanks for all people who risked their lives coming in person. Some of it COVID for enterprise. I think it was worth it.
Udi, we cannot hear you well.
Oh. Brian, can you hear me? Oh, the Zoom camera.
Try, can you try again?
Try speaking now.
Better? Or one? Can you speak, please? Rudy?
Can you hear me?
This one should be okay.
So I think this is the best microphone that's true. Zoom-wise, it seems to be working better.
Yeah, can you try saying something? Was it one?
Not picking up. Not picking up here.
We've got to.
Okay, so the microphones are decent. And, hello? Hello? Oh, this is okay. One, two, three.
Can you try again?
Now I hear you.
What? Now you hear us? Yeah.
Yeah, this was good.
Is it okay now?
Yes, now it's good.
And can I see Kobe there? Can you put his picture there?
I will.
Hi, Kobe.
Hi.
Okay, all right. Okay, so I have to look back when I want to look at Kobe about the work of Kobe and Sergei. I think there's a complete consensus. Many of the speakers who talked previously, I felt they were taking words out of my mouth, especially Philip said a whole bunch of things that I was planning to say. It's clear to what extent it's deepened and enriched this extraordinary field that has emerged. It has, as Philip mentioned, it has several different foundations. I mean, one inspired geometrically that started with Lau, and one that started with Charlie and Anand, inspired more model theoretically, and they're both still alive. Maybe there's a third one that is still not completely understood foundationally for the arithmetic or minimality of Pilo-Wilke. And to all of them would have been so much poorer without the work of Kobe and Sergei. They also have a very special style that probably many of you have noticed, and both of them listen. Both of them, when they're in talks, they're very, very attentive, and it's clear they pay attention to every line, and they follow the music of the argument. And I think mathematically also you have to be very attentive to what the structure wants. You're not going to find a field just because you want it and use it with force. You have to pay attention to it. And maybe also to people. And well, so I'll start with something more personal. And I apologize to Sergei that I'll say less about him, not because I love him less, but I just know less about him a little bit. Kobe also spoke in my meeting, and he mentioned the relationship between our supervisors, our advisors, which is identity. And then he mentioned also a relationship between our fathers, who both were interested in languages and literature. And since you already talked about parents, I felt that I have no choice except to go to grandparents. So I started speculating to myself, something we will probably never know, whether our grandparents knew each other. I think it's quite likely. If you go to around 1920, they were both close in different ways to a Jewish Workers' Party in Poland, Polecion. Later it split, and Kobe's grandfather went in the more left direction, and then his son went even further left. They're also there in a different way. I mean, Kobe's grandfather was really a central person in the party, whereas my grandfather just somehow expressed, he was on the electoral list in Vilnius, but the last one. So just indicating that as a high school teacher, so the kind of intellectual, he was honoring the party and vice versa. I think there's a good chance that they met. They were both interested in history and wrote about history and lived through a lot of history, and that in different ways, because Kobe's grandfather went much earlier to Palestine, Israel, whereas mine stayed in Europe. And in that, he may have shared experiences more with at least one of Kobe's grandfathers. It was a time where the state's attitude to you depended on the group you're in. And both of them were in groups not very favored by the state. But maybe that's for talking about in a different time. Yeah, so this is Yaakov Peterzil. And here are so two talks that you could have heard if you were around Haifa in 1934 or in 1937. Not this is the way, about something. Antifa, of course, meant something quite different in 1934 than it does today. But I think the commitment, it's not trivial to, when you're in a time of national liberation, to be against nationalism also on your side. And I think he was really committed to common living together, Arabs and Jews, in a way that didn't work out. And then his son and his grandson also spent amounts of thought and energy that I don't know if people can imagine on trying to make it better. For my part, when I felt the need to be involved in something like that, the person I called was Kobe to get some advice. I don't know if he remembers that phone call, but it changed my life completely for a few years. Yeah, so I don't know if some of that capacity of listening comes from this history. Anyhow, I should get to my talk, but I wanted to mention one other story that I didn't get to say over dinner. This is a paper of Kobe and mine. This is the only unique joint paper, if that's how you say it. In other words, the only one that has only the two of us as a set. And I don't completely remember, unlike Charlie, I don't have access to even emails of that long ago. But so I don't completely remember which conference it was, but I remember very well that Lau asked this question: if you have a no minimal structure, and well, take some sentence which is true in it, is it also true in a no minimal expansion of the reals? And I immediately loved this question, and it seems to me to be absolutely about foundations of what O minimality is. Is it the case that anything you do in O minimality you could in principle do in some way using real geometry? Or are there also domains which are completely new geometrically and maybe something can be studied there in a different way? And Kobe apparently also felt this, because as I remember it, it's Kobe, you leaned over and you told me, this is the most important problem in homonymity. And I didn't argue. I wasn't planning to work on it, but I felt it was a very important problem. However, at that time, I was reading a biography of Sofia Kovalevskaya, which is extremely recommended. And while I was reading it, yeah, I also in that conference, I think it was the same conference, there was a talk by Leonard Lifshitz, who that was described by Deirdre in her talk. Getting homonymality of kind of infinitesimal extension of the reals. And reading Sofia Kovalevskaya, at some point reading about her, at some point I got to the place where she shows that, of course, it was not a mathematical book, yeah, there were no details, but still it was stated that she found a differential equation, despite Cauchy-Kovalevskaya and the fact that there exists actual function solutions of differential equations under the right conditions, but under the wrong conditions, she found an example of a differential equation that has no actual function solutions over the reals at all. So I was very happy because I realized, so this must be the way to solve Lau's problem. And at first I wrote some technical things, of course, wrong and unnecessary and so on. But I was really pleased, both because it's connected to a question of Lau and because of the connection to Sofia Kovalevskaya that I loved, and because of the question itself. And I was especially looking forward to Kobe being happy when I tell him this. So then I either sent him an email or phoned, I don't know if you remember, and the reply was a bit surprising. He said, "Oh, this has no interest whatsoever." Do you agree? Do you remember this?
No, I must say I don't.
I remember it.
Really?
It was a bit of a mystery to me. And then about 2 weeks later, I was preparing arguments for why it's very strange to have a problem that was the most important problem in homonymity. But then, because the solution is too easy, maybe, or goes the wrong way, it loses all interest. But Kobe came around and, said, well, we can write a paper. And yeah, if you see, in fact, the proof is about 2 lines there. But yeah, I still like this paper. And it has a couple of open questions that, as far as I know, have not been addressed and still seem to me quite interesting, what I wrote in the previous slide. Fine, so now it's 11. Yeah, so definable measure, yeah, I wanted to say, just in case I don't make the whole talk, I wanted to give the sketch of the talk. So I'll start, so the whole setting will be about definable measures. And to my knowledge, in modern, somehow recent model theory, so they were studied by Kiesler in the NIP setting a while ago, but somehow not much followed. And there was a paper of Kobe and Anna and myself that reintroduced them in connection with the solution to PLAs, to a certain conjecture of PLA. Yeah, so specifically, so I think really there's a fundamental question in somehow the logic of expectation logic, the basic logic you can form out of, well, what the semantics of a definable measure, which I talk about from time to time, for example, in Dougal's birthday and in Cambridge. I'm not going to talk about it today. I'll talk about a kind of strong version of the solution. Well, I'll mention it in a bit. Then the center of the talk is going to be an analog of that in stability. So if anyone here heard my talk in ZAG, it'll be very similar to this talk, with the difference that this was conjectural. This was a conjecture in ZAG, and now it's going to, I even wrote down a proof. Yeah, then I'll mention the very strong results in this direction of Terry Tao and Alex Chevalier and Ehud-Levi. And at the very end, I'll talk about the NIP case where the state of the art is, in this connection is, yeah, somehow the case n equals 2 in several of these things is quite different from higher n, and the state of the art is due here to Artem and Sergey. Okay, I'm not sure if I'll get there, but there really the problem disappears. Well, okay, so did I discuss definable measures yet? Right, so what is a measure? Well, in general, when you have a function from a structure to the reals, you say that it's definable if, well, the inverse image you would like to say of any set is definable. You can't quite say that. And even the inverse image of a closed set is infinitely definable. In other words, if you have two disjoint intervals, then a definable set separates them. And if you're not happy with that, just think of the case where the function takes finitely many values, and that would be enough for this talk. And in this case, you just say the inverse image of each value is definable. So a measure should be finitely additive. You easily get countable additivity in the saturated situation from that, and definable. Yeah. And if you have such a measure, you can also define the expectation of any definable function or the probability of a definable set. And then you can iterate that. And so you can also get an expectation on subsets of the plane. You also get immediately a measure in the plane.
What's the definable measure?
So there, so it's definable in definable families. So if you have a family that depends on the parameter, then the function of the parameter, which is the measure with respect to the other variable, is definable. Sorry? You know, I was fighting with that this morning in my room, but there's something very, I mean, it's 12 points, and when I made it 16 points, it became smaller. But I'm really sorry about this. Maybe there's quite a lot of space here. Maybe you want to move down. Yeah, I'm sorry. I don't know if you have. Is there some? Ah, wonderful. Yeah. Yeah. So. But you can go back now. Yeah. Sorry? I can click twice, that's okay. What? Okay. Yeah, so you get a measure in dimension 2, which actually in general, for example, in the NIP setting doesn't have, it may depend on which order you do it, but in this talk, I will assume throughout that it doesn't depend on that. So it's a generically stable measure if it's NIP setting. Okay. Yeah. Now, when I was very young and I learned integrals, I was kind of okay with integrals, but then double integrals at that time they had a special symbol where the two integrals were closer together. I couldn't find it, and I was very scared of that. And then we learned measure spaces, and I was very, very pleased because measure spaces somehow were abstract enough to, I was a bit less afraid of them. And well, product measures were not a problem. So I thought, fine, so double integrals, I mean, it's just a scam. It's really all you do is you take a normal integral for the product measure. That's not true. Multiple integrals are much more general than what you can get with product measures. So if you want to think of it that way, the measure gives you an ordinary measure in the usual sense of measure theory on the type space. And if you iterate it, you get a measure on the space of two types. And the space of two types is much more, this is model theory, right? The difference between the space of two types and the space of pairs of one types. It's not the same thing. All the product measure sees is products of one types. So it's a completely different thing. And fundamental questions are about the relations between these things. Well, first some examples. So the Begg measure on a cube is a definable measure in RCF in the sense that I'm using. This is due to Kiesler and much more generally. Yeah, I think Angus was involved in some things there also, maybe later. Yeah, any ultra-product of finite structures gives a measure, but it's not necessarily definable. However, if you close the language enough, it becomes definable. In the case of pseudo-finite fields, you don't have to close the language. It's a theorem of Zoe, Lau, and Angus that it is definable. Yeah, and that can be extended also to difference equations. Okay, and the basic problem is to understand interactions. And this is true in some formal sense. I mean, so if you make a logic in which you can just talk about expectations, then everything reduces to the measure of intersections. So that. Yeah, so here, here's the type space in 3 variables, and then it can be much bigger than the various things you see for each 2 variables, for each pair of variables. What is the image of that? Well, now I'm supposed to draw a triangle. Okay. No, I don't think you need to change the lights. What did I do? Yeah, okay, so you have X, is that visible? You have variables X, Y, Z, so you think of elements, and on the line between X and Y, I may have some relation between X and Y, connecting them, and likewise between X and Z and Y and Z, but then that gives you just the boundary of the triangle, so you're saying something about it, and you would like to know, can I fill it in? Is there actually a 3-type consistent with the theory which is compatible with these things? So one obvious condition, if someone gave me R of XY and R prime of YZ and R double prime of XZ, so one obvious condition is that they should not contradict on the 1-type level. In other words, maybe R prime of XZ is just a conjunction of something with Z is red. And maybe this one, R prime of YZ, says Z is not red. They're both able to talk about Z. So obviously that'll be inconsistent. But the question is whether, assuming consistency on the 1-type level, anything you can say about 2 types is consistent. And when there's a measure around, you can ask more than consistency. You can ask what is the measure of these things. So yeah, so there are 2 possible measures that you get on this triple product. One is a canonical, it's like a product measure, but there's a notion for a fiber product, which is a soft notion. You can figure out yourself what it is. Yeah, but I wrote it in red intuitively, that a random element of this triple, how do you choose it? Well, you first choose at random an element, an X and a Y and a Z. And then having accepted your choice of the 2 1-types, P of X and Q of Y, relative to that, you choose at random a 2-type that extends them, right? And then you do the same thing for Y and Z and the same thing for X and Z, and then you don't, that's it. And then you take the product measure of these things. So that gives a completely canonical measure when there is no interaction. When these 3 binary events only have no interaction except maybe via unary events. Okay, so this is the expected measure. On the other hand, you have the push-forward measure from S of X, Y, Z. In other words, I don't know if you can see this last line. Can you see it? Yes? So you have a triple intersection. This I consider as a binary formula, binarily derived formula. It's just about X, Y, but then also something about YZ and also something about XZ. But strictly speaking, it's not binary. It has 3 variables. And you can just ask, what is the measure of that from the point of view of S of X, Y, Z? And that's something else. And then this is the fundamental question, are they equal? And when they're not equal, what is the mechanism that explains how to get from one to the other? And there was a lot of moral theory about that before measures came in the very similar setting of simple theories especially. And there, the obstruction is worth the work in itself because it's basically the compact group associated with a theory that, it started with Shelach and Laskar and Kimpile and other people. So yeah, so another question is, okay, what will be the fundamental structure for n equals 4, which we don't know yet, but this is not what I'm talking about today. Yes, 11. So I just said this, and this, and yeah. Okay, so I'll just say that if you're working over a model, these 2 measures do coincide, And that's a version of the theorem that I'll mention. Okay. Right. But now I'm going to a stronger version of this question. It's still the same problematic, but before that I was just discussing type spaces. And type spaces are only approximated by formulas. And when you take into account the approximation, it only talks about the measures up to epsilon. So you cannot find a definable set with the same measure as a given type, so to speak, but you can approximate it. And now I'm going to talk about the strong version, like as in strong minimality, namely it's for a single formula. Okay, so we fix n variables. And we're very used to doing that for n equals 2 in model theory. We're less used to it for higher n. So x1 may actually be a k-tuple in itself. I don't mind, but I'm dividing the set of variables into n classes, not into 2 classes, into n classes. Oh, yeah, okay. So an n-1ary formula is what I said before. It's a conjunction of ones that are literally n-1ary. And the formula in n variables is partition regular. So I'm defining regularity, but in several different ways. And the first is called partition regular. And that means that it implies something about n-1ary things. But aside from that, you cannot split it anymore. So it has absolutely no interaction with anything n-1ary. So so the simplest case of that is the situation of a graph of Szemerédi's lemma. So you have maybe a bipartite graph where there's some x, and there's some y, and there's some graph, and there's some edge density. But to say that it's regular, that this formula is regular, is to say that you absolutely cannot find subsets of x and of y on which the edge probability is any different. You cannot, if you try to somehow make it more efficient to work with it by dividing it into 2 somehow countries that talk more to each other in the regular set case, you cannot do it. This is Szemerédi's original discovery. In the binary case, it's even more. So now it's a ternary relation we're talking about, S of x, y, z. And okay, it only applies, as in here, it only applies when x times y. Here it only applies when certain binary things are known. And there's absolutely no way you can, if you cut down this edge, for example, you impose more constraints on it, and this edge and that edge, you will not change the probabilities. It's not interacting anymore with anything from the binary world. This is the notion of partition regularity. Yeah, and combinatorialists often call it quasi-random, but randomness is in the eyes of the beholder somehow. In other words, it's random as an n-ary relation from the eyes of n-1ary relations. It's them that are not able to say something about it, but it may be totally deterministic. So the Paley graph, which asks whether there's a square root in the finite field of x minus y, obviously it's not a random thing exactly. It's given by a formula, but it looks random if you try to say, if you're a unary creature and you try to say, well, does this correlate to x being tall and y being short or anything? No, it doesn't correlate with anything individually about x and y. It's truly binary. Okay. So that was one version of the definition of a regular formula, okay? And another definition is called counting by the combinatorialist.
What is there a precise way to define what it means to be statistically independent?
Two events are statistically independent if the measure of the intersection is the product of the measures.
Oh, okay.
Okay, it's precise. Then independent relative to is also precise, but it takes a little work to define it. I defined it intuitively in red. Okay, it means that when you take, so if you have a unary graph, like in this, okay, well, I won't say it again. Okay, so if you take into account, so relatively, okay, I said it before. Okay, so now I'm going to the next version, which is counting regular. And the reason it's called counting is that maybe you have a graph and you want to know how many triangles are in this graph. So you can make a formula saying, well, if let's say phi is the edge relation, so you say phi of xy and phi of yz and phi of xz. And you try to compute what's the measure of that. So if you just have two sides, you can easily do it. You take an x, a random x, you figure out how many, and for each such x, you figure out how many y's and how many z's, and you'll get the number, right? It's an integral over this kind of wedge or horn. But if they all connect, you don't know how to do that because maybe there's an interaction between the edges. So the regular case, the quasi-random case, is that there's no interaction. You can do it assuming there's no connection, or again, that the connection goes down to unary thing, and you'll get the right answer, okay? So in a regular graph, counting regular graph, in which the edge probability is, I don't know, is alpha, then the number of triangles will be exactly alpha cubed. Well, the measure of the number of triangles will be alpha cubed times n cubed, okay? So this is counting regular. And I'm going to specify a special case of that, which is due to Gowers, and it's at the heart of just the whole field of mathematics about Gowers norms and things like that. So it's a special case. You count something special. And actually, the something special is something that model theorists are very familiar with. When you have some description of n elements, then you can double them one at a time. In other words, I'm given A1, A2, A3, then I take A1 prime that looks the same over A2, A3 as A1, same type. Then I take A2 prime that has the same type as A2 over all the other things that I had before, and then A3. This is how you get doubling. And another way of saying it is that you have new variables, copies of the old variables, and you consider all the formulas which are exactly phi, but you're allowed to plug in either x1 or x1 prime. Okay, not both. You take so you have exactly 2 to the n instances of that. Namely, you write down phi of x1 to xn, and then you prime whichever subset you want. And if they're statistically independent, this is called doubling regular. At least I'm calling it doubling regular. Okay. Yeah, and okay, you're going to think that I'm very fussy about this, but you know, these diagrams, I wouldn't be able to do this stuff without drawing a triangle. And I'm not actually able to draw an octahedron, but so I copied it from somewhere. But that's, you know, really I'm talking about a story that really changes from n equals 2 to n equals 3. The theorem is different for n equals 2. So you have to think a little bit about n equals 3. And here's how the picture looks like. So the triangle itself is P of 2 minus. In other words, here you see it here. All the subsets of a 3-element set. So X and Y and Z denote 1 types. The 2-element sets denotes 2 types. And the 3-element set denotes a 3 type. So it's P of 2. And yeah, and if you want to pose an amalgamation problem, it's P of n minus. In other words, you take all the ones of dimension, except for the last, for the biggest one. And this terminology is due to Scheller, who really introduced this into model theory in the context of no-top. Slightly different context, but anyway, same diagrams. Now, the doubling is, now I'm doing it plus or minus instead of xi and xi prime, I'm just calling it plus or minus xi. So I double the number of variables, and I don't allow, I take all the subsets which do not contain both x1 and x1 prime. They have to make a choice. Okay? And if you draw that, then you get an octahedron. So this is the doubling of P of 3. So you see here the original problem, which was the triangle, right? So maybe you're trying to study to what extent this, you know, some information along the edges, along the one-dimensional boundary of the triangle can be extended to the whole triangle. But you have 2 to the 3 copies of this triangle somehow, and you're trying to look at the intersection of all of them. So it's like counting triangles, but it's counting octahedron. Okay. So keep that in mind, and yeah. And here's the theorem that, yeah, so first of all, and this is really essential that the definitions are equivalent, just, you know, you really want to use it, and these definitions are the same, they're equivalent. And for what we're doing, this will be enough for me. But for what the combinatorials are doing, they need to do also an epsilon version, where you say the statistical independence is only up to epsilon, and they're still equivalent. Maybe you have to go from epsilon to epsilon squared or things like that, but or epsilon to the 1/2. But anyway, they're basically equivalent, and you get finatory statement. This statement 2 here is equivalent to a version where you don't have to mention epsilon that I mentioned earlier, that over a model, the two measures coincide. Okay. There's an amazing corollary to this equivalence, that if you look at the notion of partition regularity, right, that no subset has bigger density of interact, it sounds very different if you state it for definable subsets or for arbitrary subsets, right? It sounds much stronger to say, well, I cannot do it in any way than to just say I cannot do it in a definable way. But it's actually not stronger because both of them are equivalent to counting regularity, which doesn't mention arbitrary subsets. It's just about some particular set of 2 to the n things being statistically independent. So you need to look at any subset of them to compute the measure, but it has nothing to do with expansion, so it's arbitrary sets. You can also prove this corollary in a more direct way once you see it. Okay. So in the case, so these people proved the epsilon version of regularity. That doesn't give you any example of regularity as I defined it, of strong regularity. And the first such example was done by Terry Tao for n = 2 and extended to higher n by Alex and Gilad. I'm going to state it first, it'll be a bit easier as it was in Gilad's thesis. So just for the case of pseudo-finite fields where there's no algebraic closure of any interest. So algebraic closure is just definable closure. This is not a rare phenomenon. If you give yourself a pseudo-finite field by taking an ultra product of prime fields with probability 1, there's a result of Oslem and Zoe and myself that it will have this property DCL equals ACL. But anyway, it's also interesting to look at pseudo-finite fields that, let's say, contain Q bar, and there it's not like that. But anyway, assume that it's not really important for this talk. Then every definable relation does admit a finite partition into a part which really has lower dimension in the pseudo-finite sense. The Zurich closure is lower dimensional, and a finite number of strongly regular formulas. So you can understand, so strongly regular formulas are everywhere. And in fact, you can remove this restriction, and there's something very interesting about having to go to étale covers when you do that. In other words, you have to define what n-1ary means in a more careful way, using algebraic closure, not definable closure. But I will not have time to discuss it. When it's a formula, I call it strongly. So what I defined as being regular, either of the definitions, just for emphasis. Okay, so now I come to the heart of the talk. So, so this repeats what I talked about in the ZAG talk, namely, well, I don't know, even already for NIP theories, in many ways this trivializes. Turns out that at least over a model, the measure on the space of, well, the measure algebra associated to n types is actually the same as the measure algebra that comes from one type. You have to prove it. Once you prove it, it disappears. But so all the more so for stable theories. For stable theories, you're not surprised at all to see regular formulas. And well, okay, so Marianthi, Maliaris, Shelach have some numerical results like that. Anyway, it seems too easy. It seems like the whole problematic doesn't exist. The problem is that there are not enough sets, right? If you have a strongly minimal set, it doesn't have many subsets, many definable subsets. So what are you going to measure? But there's a standard kind of solution to this kind of thing. Namely, in all minimality, indeed, a definable set has many subsets, right? The interval from 0 to 1 has many subintervals, and enough to have an interesting measure theory, enough to have cohomology theory. they have many subsets, or many partitions, if you want, many finite partitions, maybe many maps into finite sets. When you go to strong minimality, there are very, very few subsets. So if X is strongly minimal, just as finite and cofinite, nothing to measure, nothing with which to do cohomology. However, it does have a lot of finite covers. In the minimal case, every finite cover trivializes. It's just isomorphic to a union of some copies of the set. But in the strong minimal setting, in general, it doesn't. Unless it's a vector space, basically. It doesn't trivialize. So this was used by Weil for curves and suggested by Serre and then really worked out by Grothendieck to construct a ladder cohomology, which I don't really know. Here's something much more elementary is going to appear that I've not seen before, but maybe it is part of this in some way. So anyway, the idea is, okay, if there are going to be many covers, but not enough sets, let's just try to dualize everything. Let's try to dualize the notion of regularity to covers. So what's the analog going to be? So I'm stating it in algebraic geometry for varieties, but actually you can do it for stable series and even more. Anyway, the analog of a set is a finite, let's take a finite Gower cover. Statistical independence will become Gower independence. So when you have a finite cover, I'll take X to be irreducible, so you can think of function fields. So the function field of U is a finite Gower extension of the finite function field of X. And if you have two of them, you can take the join, the composite term. Maybe the Gower group is just a product, then it's called independent. And maybe they interact, and then it's not independent. And well, what is a subset of a product? What is a binary relation? Well, it corresponds to a cover of the pair, which might be a product of covers of X and of Y, but maybe not. Okay, maybe the ramification locus is somehow not unary, for example. So this is the analogy. What am I saying here? Yeah, so what does regular translate to? Well, it's clear. So you have a regular cover is a cover of X times Y, such that if you try to understand it better by just taking a cover of X and the cover of Y, it doesn't help you. So this Gower group and this Gower group are just independent from each other. There's no connection to any cover arising from unary things. That's the notion of regular. And so Szemerédi's lemma would say that any cover can be refined by a unary base change to a regular cover. And you can imagine the same thing for any n. And just for consistency, if you check it for n equals 1, it turns out to be exactly the notion of a regular field extension. So absolute irreducibility. So by calling it regular for n formulas, I'm not contradicting the standard notation. Yeah, but for any n, this is kind of what you have to prove that, yeah. Yeah. Okay. So yeah. So you have a cover. Oh, what does regularity say? That so it says that it's a cover. It's a finite cover of X times Y, such that if you take another one of X and one of Y, then these things are independent. For example, if you take the function fields, this Gower group and this Gower group don't talk to each other. Okay.
Yeah, the covers are quantified.
It doesn't matter. I'm talking about varieties, but it's up to lower dimensional things. At some point in the proof, which I'll probably not really get to, it's somehow useful to have the language of varieties, but here you can think about, yeah. So, yeah, so this is the setup. You need to talk not only about, when you talk about S of X, Y, Z, you really have to talk about the lower dimensional things implied. So you really have to talk about a system of varieties indexed by subsets of n, and along with finite maps from XB to XA when B contains A. And all the time I'm assuming that when you take the product function, so you go to singletons, you get a finite cover of the product X1 up to Xn. Yeah, so to say that it's regular means that if you make any base change by over the less than unary stuff, then it remains irreducible. You cannot touch this cover, it's a special cover. Right. So the first question would be the definition of regularity. I gave two different definitions and they're equivalent. So this is what I didn't know how to do in the Zag talk. Are they equivalent here or not? Namely, one definition, yeah. So one definition I just gave you, and the other definition is about self-interaction. In other words, you double the system. You add x1 to xn, now you have also another copy of x1, and you multiply by x1 prime to xn prime, so to speak. They're just copies of the same thing. And so, but you're not, there's no arbitrary y. You're not taking a base change with an arbitrary n minus 1 y. You're just you're looking at the self-interaction of this cover. So this cover, so, well, yeah. So the various pullbacks that you get to these things should be independent from each other, which means that any intersection is proper, still proper and irreducible. Okay. So, yeah. How much time do I have?
We started at
7 more minutes? Okay. Okay, good. So, okay, so I just essentially repeated. Yeah, so this is the theorem or lemma or whatever, but yeah, so you have a P of n variety. So it's really a bunch of varieties which are all covers of x1 times x to the n. And then you have an irreducible P of n minus variety over the part of that, the non-maximal part of that, right? So now you have, it's the same diagram, but now R1 of xy denotes a cover, so it's a finite cover, and these are the y's. So these are the x's, and these are the y's. They extend the boundary. And we're interested in another cover that lies over the interior, like x lies over all of them, and we want to say that it cannot interact with these y's. This is under the assumption that yeah, if you assume that the doubling of x is regular, is irreducible, then you want to conclude it for an arbitrary cover of x at n minus 1 level, n minus 1 level. In other words, if at n minus 1 level with an unknown y, you can make it reducible, then the doubling has to be reducible as well. Yeah, so there's some routine preparation that you need to do, and yeah. And the first lemma, okay, and I'm going to do it for n greater than or equal to 3. It's true for n equals 2, but the proof is a little bit different. And there, the groups don't have to be abelian. Here, the groups have to be abelian. So when you do your preparation, and then y has some Galois group over x, and it looks like this over this pair. So you have y of 1, 3 covering x of 1, 3, and there's some Galois group, G. And here there's another Galois group, and here there's another Galois group. But because of the interaction by a lemma, which comes up quite frequently and was mentioned also by Artyom yesterday, this kind of interaction can only come from abelian groups. So having done the induction hypothesis that at stage n minus 1, everything is regular, you get to the situation where these 3 covering groups of the y's, or these n covering groups, right, coming from all the n minus 1 element subsets of n, they interact. So there's some subgroup of the product, but in such a way that any n minus 2 of them don't interact. And the only way that can happen is when you have an abelian group, and the subgroup of the interaction is just given by the sum equals 0. That's the only way this kind of thing can happen in groups here. It's a very elementary lemma. Okay, so now that we know this, we need to define some non-trivial Galois invariant function on the doubling. So this is the limit, the fiber product of the doubling into a finite set. That's what it means to make it reducible. And I did try to play with it by hand, and you somehow get a feeling, you know, you have all these things, all these 8 things if it's n equals 3. You have a feeling that there's just too many relations to fit together, but it's not easy to do by hand. I mean, at least I couldn't do it by hand. I had to walk around and pace around for about a week before somehow it fell together. And the question is, which finite set is you're going to use in order to see the reducible component? And what it has to be is the top cohomology group of the picture that indexes the doubling of the octahedron in this case. So these pictures were just a psychological aid previously. But here, you really have to take them seriously. I mean, you really have to, it's not a trivial theorem somehow that the sphere has a non-trivial homology group, really. I mean, it's the first thing you learn in algebraic topology, but yeah, it has to be proof. And we're really using this. And I really wonder if there's another proof not using it, if there's some way to do it without noticing. Anyway, in this proof, this doubling of n, you can look at it, you can represent it as the boundary of the complex hull of the basis vectors and their minuses. That's the doubling. And you see easily that it's homeomorphic to the sphere. And therefore, you know what the top cohomology group is. And we're just going to directly define a function into that. So basically, we have the y is basically a torsor of it's a homogeneous space over this abelian group A, and here also, and here also. And when you give yourself an element of the triple cover, you're able to find a relation. You're able to find an affine function on the triple product of these affine spaces into the group. That's your relation. And you somehow have to put all of these together, and it's hard to do without having access to all 3 of these elements. In other words, the element of the triple cover, and then an element of each of these double covers. But that's cheating, because you're supposed to use just the element of the triple cover to make that irreducible. You're not allowed to use the unknown y. But you just use it anyway. And you make a cycle. Right here, I'm using both the element of the triple cover and the element of the double cover. So that's not so complicated. But then you notice that if you change, so what choices did I make here? I made some choice in each of the 8 triangles, that's fine. And then I made a choice also in each of the edges. And that's not fine, but it's a choice on the edges. In other words, it comes from a cycle that comes from codimension 2. And if you look at it, it changes things by exactly a boundary or co-boundary. So therefore, the quotient is well defined. It's just a function of A. It's well defined into the cohomology group. But since we know the cohomology group is non-trivial, that's it. I mean, we get a surjective function into a finite set, which is therefore not, well, which shows you non-irreducibility. So, okay. Yeah, so these are just analogies in the stable case and in, let's say, well, in some other cases, in simple case, in a non-stable case. It's just an analogy. But there is one setting where you can compare the 2 of them, and it's the setting of pseudo-finite fields, or of taking a field and adding an automorphism to it. And in that case, both of them make sense, and this gives you a proof of the Tau Chevalier-Levi theorem. Many of the components were already in the, well, in the proof, which is by in other proofs. But this one just purely reduces the algebraic geometric statement to a pseudo-finite field statement. So this is something basically due to X, brought out by Yarden and Fried. So if you have a Galois cover, right, so just a finite morphism of varieties, and you can think of it that X is Y modulo the action of a finite group G. Then over a pseudo-finite field, this cover really turns into a partition, right? It's a difference level. You can write down sigma of Y, structural automorphism, equals age of Y, element of the Galois group. And this has to partition Y, and then you can push it forward to S, and it still partitions X according to the conjugacy classes of G. Okay, so suddenly these covers actually turn into partitions. You can compare these 2 worlds, And indeed, you can check that the doubling equivalence gives you, okay, that you get new proofs of these. So it's quite interesting because somehow the combinatorial proof uses Cauchy-Schwarz in a certain way, which Gowers introduced, and I guess maybe Rödl-Skokan as well. And it feels very analytic. It feels very mysterious to people like me. And this one just uses a little bit of algebraic topology instead, but nothing analytic. So it's not clear at all how it is that, I mean, how to see that they're the same. Yeah, this was supposed to be about the implication. And well, yeah, so I'm out of time, right? Or yeah, okay, so thanks very much. I'll stop.